Okay guys, today we're going to be finishing off the rest of our titrations lesson. We'll be starting at, I think it's like slide 16 and going through the rest of it. We're not going to be doing any of the pH stuff today that we did on the last lesson, but there will still be some solution stoichiometry type problems. Okay, so just a reminder, when we're talking about equivalence points, what we mean is the point in the titration where the moles of the analyte and the moles of the base are equal, which essentially means that the moles of the acid and the mole of the base are equal. If the titration involves both a strong acid and a strong base, then those will neutralize each other and you'll have an equivalence point occur around a pH of 7. So if that's the case, then that's just like our normal net ionic equation that we would have. So obviously you have your acid reacting with your base in a normal neutralization reaction, making the salt in the water. If you were to show how that like dissociates, both the acid and the base ionize or dissociate, break apart into ions when they're in solution. And so what we would end up with is just the hydronium and hydrogen ions making the water. So that's why it just has a pH of 7. You don't need to know why it has a pH of 7. All you need to know is that if you have a strong acid and a strong base in a titration, the equivalence point will be at a pH of around 7. If you have a weak base with a strong acid, the fact that the acid is stronger than the base pulls the equivalence point down towards a more acidic pH. So the pH of the equivalence point will be maybe like a 4 to a 6, something that's slightly acidic, instead of the neutral pH equivalence point that we would have if the acid and base were equally strong. On the other hand, if you have a weak acid and a strong base, then the stronger base is going to pull up the equivalence point towards a more basic pH. So you might see a pH of like 8 to 10 as your equivalence point. And that's just because at that point, you've got essentially an imbalance that's happening between the strength of the acid and the strength of the base. Okay, we'll talk more about that later and how to read titration curves to identify what type of acid and base you're dealing with. But first, we're going to get on to another type of calculation, which is calculating equivalence point volume. So the equivalence point, again, where that the moles of acid and base are equal, the equivalence point volume that we're talking about is how much titrant is used at that point when you hit the equivalence point. So that should ideally be what is the volume of titrant that you have at your end point. So in order to do this, of course, like everything, we start with our balanced chemical equation. It will be a neutralization reaction because it is still a titration. Then we'll start with our C equals N over V. So this time you'll be starting with your analytes concentration and volume. Then you will mole ratio back to the titrant, C equals N over V again, this time finding the volume. So again, this is an example of what that would look like that you guys can go through at your own pace whenever you want. We will go through the first question here together, and then you guys can try the next two on your own. Okay, so for question number 1, we have phosphoric acid, which is H3PO4, reacting or being titrated into potassium hydroxide, so KOH. So we're going to make water and K3PO4. And then we balance with a 3 there and a 3 there. Then it tells us we have 1.5 molar acid, 3 molar base, 20 milliliters of the base, and we want to know how many liters or milliliters, could be either or, of our acid was titrated into the base in order to reach the equivalence point. So that was step one. Step two, we'll do C equals N over V, again, just starting with whichever one it gives us two values for. So C equals N over, don't forget to turn your 20 milliliters into 0.02 liters, and then multiply. So 3 times 0.02 is 0.06 moles. So that is our KOH. And then we're going to set up a mole ratio between our acid and our base, which is a 1:3 ratio. Plug in our 0.06 moles, cross multiply, and divide. And get 0.02 as our, sorry, not concentration, moles of our acid. And then we go back to C equals N over V. This time, though, instead of solving for concentration, we are given concentration and we'll be solving for volume. So in order to do that, don't forget you must move whatever's on the bottom of this fraction over here. So we multiply by V, which leaves us with 1.5 V equals 0.02, and then we divide by the 1.5. Which is 0.013 repeating liters, or 13.3 milliliters of your acid. Okay, so try the other two questions and then come back and check your answers. Okay, for the second equation, we have hydrogen iodide, also hydroiodic acid, reacting with calcium hydroxide, of course, making water and calcium iodide, balanced with a 2 in front of our acid and water. Then we'll start with our C equals N over V, in this case for the acid, and solve for moles. You'll get 0.0875 moles of your hydroiodic acid. Set up a mole ratio between that and your base. It is a 2:1 ratio. Cross multiply and divide and get 0.04375 moles of your base. Plug that into C equals N over V to solve for V. Of course, you do that by dividing the moles by the 1.8, and you will get 0.0243 liters or 24.3 milliliters of your base. Okay, and then for the last one, we have bromic acid, which is HBrO3, reacting with barium hydroxide to make water and barium bromate. We'll start with C equals N over V, in this case for our base, since that's what we have volume and concentration of. We multiply and get 0.0375 moles of the barium hydroxide. Then we set up a mole ratio between our acid and our base. It is a 2:1 ratio. We'll plug in our X and our moles of barium hydroxide, cross multiply and get 0.075 moles of the bromic acid. Then we go back to C equals N over V to solve for V. Of course, don't forget, you've got to move the V to the other side and then divide by the 0.3. So you end up with 0.075 divided by 0.3, which is 0.25 liters or 250 milliliters. By the way, for all of these problems, I would always recommend converting your volume into milliliters, as on the unit test, you're definitely going to have to be able to do that, and the quizzes. Okay, so the next thing that we're going to be looking at is some titration curves, which is just the graph of the line when you essentially graph the pH and the volume of the titrant added to the analyte on your X and Y axis. If you are titrating a base into an acid, your graph will start low because your analyte is acidic, and then as you add more of the base titrant, the graph will go upwards to show that the analyte is getting more basic as you add the base to it. If you're titrating an acid into the base, that means that your base is the analyte, so your curve will start really high to represent the basic pH of the analyte, and then it'll get lower as the pH drops because you're adding the acid to it. Usually your curves are kind of like S-shaped-ish. You'll see pictures of them soon. The pH changes really slowly when you first start adding the titrant, and it'll start changing more slowly as you move further away from the equivalence point. But there is an area of the graph where the pH will change very, very rapidly, and you'll see like a near vertical line. And right in the middle of that vertical line is where you find your equivalence point. So you can read the equivalence point right off the titration graph just by finding the middle of that vertical portion and then going over to the y-axis to read the pH off of that. Again, if you have a weak acid and a strong base, you expect an equivalence point with a pH above 7. Weak base and strong acid will have a pH equivalence point below 7. And if the acid and base are both strong or both weak, then you'll have a pH equivalence point right around 7. If you have polyprotic acids or bases, there will be multiple equivalence points, and it will look like kind of like steps going up or down. So this is what these kind of graphs could look like. So if I was to ask you about an not equivalence point, a titration curve, I would ask you, what is the titrant, what is the analyte, and how strong are they? So the first thing that you can determine is the relative strengths of your acid and base just by looking at the equivalence point. So in this case, we've got this kind of vertical section here. The equivalence point would be right in the middle of that. And in both of these cases, that is right around 7 for a pH. That tells me that I have a strong acid and a strong base involved. Then I'm going to look at where the graph starts. If the graph starts really low, that is an acidic analyte. If the graph starts really high, that's a basic analyte. And then where the graph ends tells us the pH of the titrant. So if the graph ends, as we move from left to right, if it ends really low, that means the titrant was an acid. If it ends really high, that tells us that the titrant was a base. Now in this case, it tells you that we're adding NaOH and adding HCl. On a quiz or a test, it won't tell you that. It'll just have like volume down there. It won't tell you what the volume is of. So that's why you do need to be able to read it, okay? In this next example here, again, we look for the vertical section. Right in the middle of that would be our equivalence point. We're looking at like a 5, 5.5, which means that we have an acid that is strong and a base which is weak. Then I look at where the graph starts. So in this case, it's starting high. That tells me that my analyte is a base. It's ending low. That tells me my titrant is an acid. Over here, we've got another equivalence point that is low. So once again, a strong acid and a weak base. This time, however, the graph is starting low, which means this time my analyte is the acid. And then it's ending higher, which tells me that my base is the titrant. And then lastly, we've got, in both of these examples, equivalence points that would be above 7, which means that we have a stronger base and a weaker acid for both of these examples. In the first one here, I'm starting high, so that means my analyte is the base and my titrant is the acid. In the other example, I'm starting low, so that means the analyte is the acid, and then I'm ending up high, so the base is the titrant. This is what curves would look like if you had a polyprotic acid or a polyprotic base, where you see these kinds of multiple steps. If you see a graph like this on a worksheet or a test or a quiz, you don't have to know the relative strengths of the acids and bases. You don't even have to know which one's polyprotic. All you have to know is that there's a polyprotic substance that's involved as soon as you see these steps. Okay, so you would just have to say polyprotic. If both the acid and base are weak, once again, they're like equal in strength, just like a strong acid and strong base. So they will have equivalence points around 7, but the curve won't be nearly as steep as what we've seen in all of the other examples. If you see this like really weak looking curve, that just means that both the acid and base are weak. Okay, so I would like you guys to go through these 5 graphs on the bottom and see if you can tell me what the analyte is, so if it's an acid or a base, what the titrant is, and how strong they both are. If it's polyprotic, just say it's polyprotic, okay? Okay, so pause if you haven't tried that, and I'll just go through now and kind of take this up. But this is kind of similar to the type of question that you would see on a quiz or test. So the first graph down here, I can tell that I have a base analyte. So my analyte is a base, my titrant is an acid, and because the pH of my equivalence point is below 7, I know that it is a weak base and a strong acid. For the second graph here, my analyte is an acid, my titrant is a base, and because the pH is above 7, I know that my base is strong and my acid is weak. In the next example, the middle one here, I have an analyte that's a base, a titrant that's an acid, and they are both strong. In the next one, my acid is the analyte and my base is the titrant, but they are still both strong. And then in the last one, it's polyprotic. Don't worry about this. You are not going to be drawing any titration curves this year. So just skip that slide. Okay, the last thing that I want to talk about is titration indicators. So anytime you're doing a titration, you need to use some sort of pH indicator to show you when you've reached the end point, because you can identify the end point by a color change that happens when the pH changes. And in order for there to be a color change when the pH changes, you need to be using a pH indicator. You do want to pick an indicator that changes color around where you're expecting the equivalence point to be. So we choose indicators to identify the end point based on the equivalence point, that theoretical area where the moles will be equal. So yeah. So the 2 most common indicators are bromothymol blue and phenolphthalein. Bromothymol blue will be yellow if it's acidic, green around neutral, and then blue when it's basic. So it has the most notable color change happening when it goes from yellow to blue, kind of around 7, with right at 7 being green. So anytime you have a titration where you have both a strong acid and a strong base, or a weak acid and a weak base, then you would choose to use bromothymol blue. If you are dealing with a stronger base and a weaker acid, that means your equivalence point is going to be in the range of like 8 to 10-ish. So you want to choose an indicator that's going to have a color change around 9. So that is when you would choose phenolphthalein to go from clear to pink as you go from below 9 to above 9. So yeah, that's what I'm talking about here, the fact that phenolphthalein is the best choice when you have a weak acid and a strong base. If you have a weak base and a strong acid, then you're going to have a color change happening, between 6 and 4, at which point you are going to want to pick one of the methyls as your pH indicator, so either methyl red or methyl orange. They're both red below their pH indicator change, and then yellow above it. So on a test or quiz, you will have to be able to tell me, based on either a titration curve or me just telling you what 2 compounds are being titrated, you will have to tell me which indicator to use. You will not have to differentiate between methyl red and methyl orange, but you'll have to know if you should be using bromothymol blue, phenolphthalein, or one of the methyls. So take a moment now to see if you can figure out for each of these titrations which indicator you should be using. So pause right now and figure that out, and then I'll go over it. So for the first one here, lithium hydroxide, that is a strong base. And then you've got your H2S, which is hydrosulfuric acid. As it tells you here, strong acids include hydrochloric, sulfuric, and nitric. Most other common acids are weak. So that means that H2S is weak. That's not sulfuric acid, that's hydrosulfuric acid. So because I have a strong base and a weak acid, I should be using phenolphthalein. Then we have sodium hydroxide and nitric acid, which it tells us here is a strong acid. So those are both strong, which means I should be using bromothymol blue. Acetic acid, that is vinegar, and ammonia, which is a weak base. So those are both weak. I should once again be using bromothymol blue. And then for the last one, hydrochloric acid, we're told that that is a strong acid. Ammonia, we know, is a weak base. So I should be using one of the methyls, methyl red or methyl orange. Okay, so that is it for titrations. Let me know if you have any questions.